Combustion analysis, it says here that it's going to be compounds that contain carbon, hydrogen, or carbon, hydrogen, and oxygen, but this same process can be used if that third element is something different. Like maybe it's a nitrogen-containing compound. Okay, you can still use this same process we're going to look at here together to do this. All right, so kind of the steps we've already talked about are listed here. But we're going to go ahead and go through this one and do this. This is the longest version of a combustion analysis problem that you might have, okay, which is find the empirical formula when it contains carbon, hydrogen, and oxygen, and then also find the molecular formula, okay? So we've got a 2.0714 gram sample of a hydrocarbon that has carbon, hydrogen, and oxygen. We get 1.928 grams of water, 4.709 grams of CO2. In another analysis, we found that the sample's molar mass, whoops, there's a typo. Okay, for sample is 116.16 grams per mole. We want to find the empirical and the molecular formulas. Okay. Doesn't really matter how you go about solving this problem in terms of how you organize your work, but those steps, okay, grams of CO2 to moles of CO2 to moles of carbon, okay, find your mass, okay, all of these steps need to be shown somewhere in your work. Okay, I like to start with CO2 because the carbon is actually going to come first in your formula. So we're going to go 4.709 grams of carbon dioxide, change that into moles. Using our molar mass of 44.01. Somebody last period said it would probably be helpful to memorize those molar masses for CO2 and water. I mean, yeah, but even if you don't try to memorize those, we use them so much they're probably going to get stuck in your brain. Okay. And then we talked about this 1 mole of carbon for every 1 mole of CO2. Okay, and just like with a straight up regular empirical formula problem, I like to take quite a few digits here, 4.709, right? I got 0.10, let's make this 700 moles of carbon. Because this one does contain oxygen, I'm going to go ahead and change this into grams. I'm just going to kind of do it right here just to kind of save some space. Plus my mole value is already in my calculator. So I can just multiply by the mass of carbon, 12.01, and I get 1.285 grams of carbon. Okay. Same thing for water. We're going into moles and then also into grams of hydrogen, 1.928 grams of water. 1 mole of water is 18.02 grams of water. And then 2 moles of hydrogen for every 1 mole of water. Okay, kind of same thing here as to how I like to set this up for myself. Yikes. Okay, I get 0.21398 moles of hydrogen. And then if I go to molar mass, 1.008 grams per mole, pretty tiny, 0.2157 grams of hydrogen. Okay. Now, here's where we are doing our new part. To find the mass of the oxygen, we have to find it by difference. So we're going to take the total mass of the sample, 2.0714 grams, minus the mass of the carbon, 1.285 grams of C, minus the 0.2157 grams of hydrogen, which should give me 0.5707 grams of oxygen. I don't need a mole ratio to figure out how many like moles of oxygen I have in a compound because we've already separated it out from the compound. So all I need here is to turn this into moles by using the molar mass of oxygen, 16.00 grams. This one is going to turn out to be our smallest number of moles, 0.03567 moles of oxygen. At this point, it's just a straight empirical formula problem, like we've already been doing. We're going to divide by the smallest number of moles, 567. That gives me 1 here. Okay, in the interest of time, I'm going to go ahead and tell you this is 3 for the ratio for carbon and 6 for the ratio for hydrogen. Okay, it's like 2.99 and 5.99. So that means we've got C3H6O. Last part asks for molecular formula. What do we do for that? Well, it's easy, right? At this point, we're going to take that mass from the problem, which is 116.16 grams per mole, and we divide by the mass of our empirical formula. I'm going to go ahead and do that real quick. Ooh, not 13. 3 times 12.01 plus 6 times 1.008 plus 16 gives me 58.078 grams per mole, which is 2. So this will be C6H12. Ooh, that's a weird O. Let's try that again. O2. Yes, these are a little long with this oxygen-containing compound process, but we don't need a lot of these problems to figure out what to do, right? The next 3 pages in the practice are going to be the combustion analysis, but there's really not that many in there. Okay? Sweet. Excellent. I like these. I like the puzzle of them.